Hello, everyone. Welcome back to the third session this morning. We have Vincent Tan from NUS. Vincent is a associate professor in Department of Math and Department of Electrical and Computer Engineering at NUS. He got his PhD in Electrical Engineering and Computer Science from MIT, and he got his bachelor's and master's from Cambridge University. He received several awards for his research and teaching, including Jin Ao Kong Outstanding Doctoral Thesis Prize, NUS Young Investigator Award, Singapore National Research Foundation Fellowship, Engineering Young Researcher Award, Engineering Educator Award, and Annual Teaching Excellence Award. Vincent serves on the editorial board of IEEE Transactions of Signal Processing, Machine Learning, and Statistics, as well as IEEE Transactions on Information Theory. Without further ado, Vincent, the floor is yours.
Thank you very much. Can everyone hear me? Behind? Yeah, okay, great. So today I'm going to talk about, actually I have 3 talks, right? So I have 3 hours. So I was thinking that I'm going to talk about several aspects of multi-arm bandits that my group and I have worked on over the past few years. And in the first third, I will talk about fixed budget best arm identification in linear bandits. This has got nothing to do with risk, unlike the title of my abstract. In the next 2 parts, I will talk about risk-aware bandits. But I think that this part of the series is it can be presented in a very didactic manner for the students to understand. That's why I chose to do this. And this is a good lead up to what is bandits and what we have done. So here in this part of the talk, I will be talking about fixed budget best arm identification in linear bandits. And this is joint work with my PhD student, Junwen Yang at the National University of Singapore. This was presented as last year's NeurIPS. Okay, so I want to go slowly, and that's why I'm doing this writing stuff. Okay, so in this problem, here's the setup. Okay. We have a set of arms, a finite set of arms, which I call the arm set, and they are K arms. Right, 1 to K. I want to emphasize that we are dealing with a finite arm set. So each arm, I, belonging to K, is associated to an arm vector, AI belonging to RD. Okay, so each I is associated to a vector in RD. So the arm vectors form a set. Arm vectors are in this set, A1, A2, all the way up to AK. And they are all vectors in RD, so it's a subset of RD. I want to emphasize, because I'm sure I'll get this question, that these arm vectors are known. I'm not sure how many people know about bandits, perhaps half of you, but I don't know how many people know about it in a very deep way. So I'm going slow here. Okay. So the dynamics of the problem is as follows. All right. At each time T, right, the agent, there's of course an agent around. The agent chooses an arm AT. So this is a number between 1 to K, and he or she observes an observation, right, which we'll call XT. Some people call this reward, but just an observation. Theta star AAT, so that's an inner product, I'm sorry, plus 1 sub-Gaussian noise. So that's the linear bandit model for those who know, right? So this is a linear bandit model. And here are some features of it, right? So these are, of course, as I mentioned above, known. The arm vectors are known, and AT is the choice that we make at time T. Theta star is an unknown vector in RD, of course. And as I mentioned, this is 1 sub-Gaussian noise. Okay. So here, all this evolves across time, all right? And that's what we observe. So we will use this script E to denote the set of all instances, defined above. Right? And this is characterized by, okay, A1, the arm vectors A1 up to AK, as well as the unknown parameter vector, as well as, this one here, the variance proxy of the sub-Gaussian noise, okay? So that is a setup of linear bandits. And so what is our objective? Objective in this whole work, all right? We are interested in the fixed budget BAI problem, fixed budget best arm identification problem. And what does that entail, all right? So here the number of arm selections, which we will denote by T, is fixed. Okay, and we would like, of course, to find the best arm. The best arm is defined as the one that has the largest expected value. The expected value is this, right? Okay, so we want to query in this particular manner so as to find the arm that maximizes this. And I will try to make this precise in a moment. So this is in contrast to something that you might have seen and worked on previously, fixed confidence. So that's another paradigm. In the fixed confidence setting, you fix the error probability delta, and you let error probability delta go to 0, all right? And you try to find what is the best stopping time that you can achieve. But that's not what we are doing. We are keeping the number of arm selections as a fixed number, and we want to try to minimize the error probability, which I will define very shortly, okay? So what are we meant to design? We are meant to design an online algorithm. And the online algorithm that we will design is denoted by pi. It's a sequence of functions, t running from 1 to t, okay? And it depends on, okay, pi t actually depends on previous arm pools and observed rewards and observations, let's say. Okay. Right, so each pi t is a probability distribution that depends on previous actions or previous choices, the A's here, as well as the observations, at minus 1, xt minus 1, all right? So we would like to design, our ultimate goal, okay, is to design an online algorithm, which is the sequence of functions, design pi, that achieves or approximately achieves, that does as best as possible, okay, in minimizing the error probability, okay? So that is defined as the probability of my final recommendation, which I will denote by I out t, is not equal to argmax. What is argmax over all possible arms that yield a certain reward, okay? So some comments here. So this is basically the unique, let's say there's a unique best arm. Okay, that is the best arm, the index of the best arm, and that is our prediction, our estimate, if you wish. Okay, so we would like to minimize this error probability. We'd like to design an online algorithm that does this job. Okay, hopefully that is clear. All right. Okay. Okay, so before we discuss, so the agenda for the talk is as follows. We will design an algorithm that does pretty well in terms of minimizing this. We will derive a lower bound on, we'll derive a minimax lower bound, and we'll compare the performance of the algorithm to the minimax lower bound. That is the agenda. But before I talk about this in more detail, I want to basically describe, I want to give a few observations first, okay? Observation. This observation is not the same as this observation, all right? It's just my observation. The agent's observation is different from my observation. Okay, this is observation 1, right? If the arm vectors A1 to AK, okay, all these observations will be used as insights to design our algorithm, so they are not useless observations. If they do not span RD, all right, then of course, basic linear algebra tells us that we can find a matrix, okay, B. Maybe I will change this a little. D times D prime. D prime is less than D. such that the transformed arm vectors AJ equals to B transpose AJ. Okay, let me see whether this works out. All right, so this is D prime times D times D prime. So this is D prime times D. So this operation is okay. All right, so if we create these new arm vectors, all right, such that now these new arm vectors will span Rd prime, a lower dimensional space. And you can obtain this matrix B via Gram-Schmidt, for example. How to spell Schmidt? M-I-D-T. Okay, so the picture is as follows, all right? So you have a 3 arm vector, say you have 3 arm vectors here. K is just 3, and say they live in R3 as well. So this X3, X2, X1. And you have 3 arm vectors, okay, maybe this color. And they live in some lower dimensional space. For example, they are on the X1, X2 plane. All right, so you can just operate as if you are on the X1, X2 plane. Okay, there is A1, A2, A3. All right, so there's nothing interesting here. We don't have to use this. We don't have to use this dimension. All right, so that's what it's saying. Hopefully, this is very clear. All right, so another technical tool that we will need is very simple, and that is the OLS, ordinary least squares estimator. Okay, so if we have this is meant to be observation 2. That was meant to be observation 1 above, basically dimensionality reduction. We have a bunch of arm vectors, A1 up to AN, okay? And we observe the corresponding, say, rewards, X1 up to Xn, which are real numbers, obtained through the inner product, okay? So A1, let's say that we have done the dimensionality reduction as I mentioned above, and A1 up to A1 ... AN span RD. Okay, say we are already in deep, we have already done the above dimensionality reduction. Then you can form the following simple estimator for the unknown parameter, the least squares estimator. Okay, given by A. So no regularization is needed here because we have this property. Okay, so this is the OLS estimator, and here because of this property here, all right, V here, the Gram matrix, right, is invertible. AT transpose, this is invertible. All right, so we are now, so this is all basic linear algebra here. Okay, this is basically the pseudo inverse, I guess, right? This is invertible because A1, AAN span RD. So that's the OLS estimator. All right, so now we want to, in order for us to design a proper algorithm, we want to be able to state or recall some statistical properties of the OLS estimator, ordinary least squares estimator. And these statistical properties will motivate the design and analysis of the algorithm that will turn out to be minimax optimal. So this is a simple theorem that doesn't really need to be proved because it's really simple. All right, if A1 up to AN are deterministically chosen, we would like to make some statement about the OLS estimator above, deterministically chosen. Then, okay, for every B, we can think of B as some direction and delta bigger than 0. We would like to estimate the probability that in a certain direction, theta hat, which is the OLS estimator, theta star is the ground truth unknown parameter. All right, so we are looking in the B direction, bigger than 2 V inverse squared log 1 over delta. This is a very simple result. Is less than delta. Okay, so this norm here, B V inverse squared, this is the Mahalanobis distance, B transpose V inverse B. All right, so here we have some concentration bound for the OLS estimator in any direction B. Okay, so B manifests itself here as well as there. All right. By looking at this particular concentration bound, and in particular this term right here, the weighted norm or the Mahalanobis distance, this motivates us to design a proper algorithm that will minimize the error probability in phases. Okay.
Yeah. Well, Vincent, I have a question.
Yes.
So in a bandit setting, this V matrix need not be invertible if I choose the same arm, right? How do you ensure invertibility?
Okay. In the course of the algorithm, we are going to do Gram-Schmidt. Okay, so that will ensure invertibility at each point in time.
So in each round, you're going to do Gram-Schmidt.
Yes, that is the key, right? That is the
Alright.
key to actually also achieve minimax optimality. All right, so yeah, that's a very good question. And I should have emphasized that in our algorithm, which I have not presented, we are going to do dimensionality reduction to exploit the fact that this V here is going to be invertible. Okay, right. So we are inspired by this term right here. And based on this, we will design a particular algorithm. Okay. So aim. We would like to find, at this point, a probability distribution.
Vincent, I have
Yes.
another question. So why do Gram-Schmidt instead of just adding a regularizer? Why is it strictly necessary that you have to go through this path?
That's a good question. Why not add a regularizer?
Or hopeful we just add a lambda times ID term and just work with it instead of going through a compute intensive scheme in each round.
Well, it's actually not very computationally intensive to find this B matrix each round. Okay. And the key here is that in the course of the algorithm, we would want as few phases as possible. The phases should be roughly log of the dimension D, all right, instead of log of the number of arms K. So by doing this Gram-Schmidt operation, we can basically reduce the dimensionality to exactly what we want at each point in time so that we achieve minimax optimality. I'm not sure whether we can do that if we add a regularizer.
I'll have to look at the algorithm. The other question is like, not sure I understand why Gram-Schmidt is not compute intensive. Like if D is large, maybe small d, okay, but
D is assumed to be small.
D is small.
Yeah,
Okay.
D is assumed to be small. D is, so we are operating in the regime that D is smaller than K, which is also, and T is large, all right? This is meant to be the regime of interest here, okay? Right, okay, so I'm not always looking up like that because I need to look down. So in case you have any questions, just shout it out, okay? Right, so we're going to find a probability distribution, all right? Okay, I'm going to use another symbol for probability distribution. In the paper, it's pi. Pi will conflict with the policy, all right? Probability distribution Q, that brings us from the arm set I, this is the arm set, arm vector set, to 0, 1, okay? That minimizes the following. Okay, this is meant to be Q, GQ, max I in K of AI, VQ inverse squared. So we are inspired by this particular term here. That is what we want to minimize because that is kind of like a deviation away. We want to do this uniformly in each direction. All right, we want to do this in each particular direction that of our arm vectors. Okay, and I'm owing you the definition of this VQ here. It's just a certain weighted norm, weighted matrix, QI, AI, Q of AI, AI transpose. Okay. So this has a name. This is known as G optimal design, which is very well studied, both its theoretical properties as well as its computational properties. So this function here that we want to try to minimize, okay, so what we want to do is to minimize this across all probability distributions Q. This function GQ here is related to the confidence bounds confidence bounds in the linear BAI problem. In the linear BAI problem. Okay, so we want to minimize this uniformly across all different directions spanned by the arm vectors at a particular phase. But now let's just talk about the arm vectors. So this is these are arm vectors. We want to minimize this part here because that's a deviation. And so we'll try to find a probability distribution that does the job. Okay. Okay, so now we have all the observations and ingredients to state our algorithm, and our algorithm can be just presented pictorially. Okay. So max min definition. Okay, I will give it later. Right. Roughly speaking, okay. So this is what we want to achieve. This is the probability that we want to minimize. Okay. Very soon, I'm just going to give you a sneak peek. We're going to maximize over all possible instances here and then minimize over policies. So that answers your question. Okay. Right. So now let me move ahead and talk about the algorithm, which is not very creatively called. It's basically optimal design based. The design comes from the G-optimal design. Optimal design based linear BAI or best arm identification. In short, OD-Lin BAI. And this is the state of the art in this area. Okay, as I will tell you, I will compare this to various other algorithms that are out there very shortly. So our algorithm can be illustrated using a picture. All right. So this T in N is fixed from the very beginning, and we are going to operate in log2D phases. Okay, log2D phases. So this is the start. This is the end. The end is T. All right. So as I mentioned, we are going to think of D to be much smaller than K. And so what we have is the following. All right. We are going to split this into phases. This is the phase 1, or say round 1, round 2. Roughly speaking, the length of each phase is T divided by log2D. This is 2D divided by log2D, etc., etc. Okay. 3T divided by log2D, etc. Okay. So in the first step, what do we do? All right. So what we do in the first step here is very special. It's very special from what we do in subsequent steps. Everything we do in subsequent steps is the same. What we do in the first step is a little bit different, but the difference gives us the minimax optimality. Okay, so that is what I want to mention. I want to illustrate the first step and one generic step later on. First step, R equals to 1. Okay, so we have this large number of arms. As I mentioned, K is large, D is small. Okay, so this K, this is basically our K arms. And each of the arms, let's say, is represented by a large circle, all right? We have a large number of arms, okay? So that is our, as with any elimination type algorithm, we start with a certain active set A0, okay? All right, so each one of these represents high dimensional arm vectors, AI belonging to RD, okay? So, if necessary, if these vectors do not span RD, what do we do? I have already given you observation 1. We do dimensionality reduction. We, through some means, find a Gram matrix B1. The one here, the index 1 here stands for first phase, B1 transpose A0I. And then we create a new instance, okay, with the same number of arms, and we basically reduce the dimensionality of each one of these arms so that it becomes lower dimensional, but the same number of arms, okay, lower dimensional, so on and so forth. All right, and now these arm vectors will then be called A1I. Okay, what we do now is basically, okay, No problem now. We can just do G optimal design because now we span RD. G optimal design. We find a particular distribution Q1. Okay. And now we're going to pull arms according to, this particular distribution. There is, I'm lying here a little bit because we need to do some rounding, right? But the rounding procedure doesn't affect the guarantees too much. Okay, we are going to pull arms according to the distribution Q1, all right? And each arm is going to be pulled, you can calculate T1 times, okay, which is roughly equal to, because this must be an integer, QAI into T divided by log 2D, all right? Because the phase is log 2D, all right? So, good. So, what do we do next? We're going to pull arms according to Q1, according to the proportion Q1, and then we are still in the first phase. We are going to do elimination. We are going to retain the best, empirically the best, D over 2 arms. Okay, what is the meaning of best? With the highest, say, empirical means. Okay, so let's see. We probably have to do a ceiling here. Okay, so here, we start off with K arms. We are retaining only D arms, or order D arms. We are very aggressive at the very beginning. What are we left with? We are left with an active set with very few arms. So now we are at active set A1. This A is conflicting notation with my arm set. Okay, so sorry about that. This is my active set. Okay, so that's A1, right? We have vastly eliminated lots of arms from K to D over 2. Okay, so instead of 1, let's call it AR minus 1, okay, where R is a generic round number, okay? So here R is between 1 and log 2D, which is the total number of phases. So what do we do now? All right, we do, again, dimensionality reduction through Gram-Schmidt, dimensionality reduction to form AR, which is equal to B. Hopefully these indices are right, AR minus 1I. And now we have, again, smaller arms, okay? And we are going to eliminate the smaller arms. Let's say the arms look like, we have the same number of arms, but we have smaller arms. Same number, but say smaller. And at this point in time, because now we are already in steady state, we are not in the first phase, okay? So we are going to again, we are not going to eliminate too many, but we are going to again pull arms according to G optimal design. According to the G optimal design, and each arm will be played TR times roughly T divided by log 2D, which is the size of each phase, QR, AR, I. Okay, and now how many will we retain? Okay, how many arms will we retain? We will retain half of what we started off with. At the very beginning, we were aggressive. Now we are not so aggressive. We will retain half of them. Okay, and that is our active set AR. We have retained half. So here, half of arms retained. And the ones we retain are, of course, the empirically best ones. So that's the entire algorithm, ... until we have one single arm left. And this works, all right? I have not said what is meant by works, but at least we will end up with one arm, all right? So it's not uniform. It is according to a certain distribution that is dictated by the G optimal design. You basically do uniform in each phase. Yeah, but because we are here, we are in linear bandits, right? And we are motivated by this theoretical guarantee here. So we have to sample according to a special distribution.
Yeah,
Okay.
Vincent, I have another question. Why this asymmetry? Why do you need to cut d/2 arms in the first phase and keep on halving it later? Or let me
All
put
right.
it this way, why not just keep halving the number of arms starting from phase 1? What's the
Good
problem with
question.
it?
Okay, and this is a good question. If I answer it now, I'm going to tell you everything. All right, so well, let me just answer it now. Essentially, we want a guarantee of this form. Okay, the error probability is scaled as e to the minus t. This is very natural. We are in the large deviation setting. Some hardness parameter here. All right, and if you do what you said here, you will have a log 2k. All right, because you have this number of phases, log k phases.
Successive rejects.
Yes.
Yeah.
This we want to improve to log 2d. All right, then d is smaller than k, so this is more favorable.
And you have a lower bound of the same order,
Yes.
is it? The lower bound has log d instead of log k.
Yes, exactly.
Okay,
Exactly.
I'll wait
so
for the.
this is what we are hoping to get. This is what we're hoping to get, and this will be suboptimal. This is what other people got. Okay, so I'm telling you the story now.
Who came up with this? I'll cut d/whatever 2 arms in the first phase and.
Sorry.
Intuitively,
cut from K
yeah, in
to-
the first phase, if I cut, I'll get log 2d is quite non-trivial to imagine. Yeah.
Yeah. So this requires a little. The first phase has to be analyzed in a slightly different way compared to the steady state phases. Okay. You could chop things up in a different way as well. This you can improve a few constants because our constants are horrible. All right. But this works in order to get the thing that has just disappeared, the guarantee that has just disappeared. All right, so let me write down the theoretical guarantee in a more formal way. Theoretical guarantee. So this looks very much like a standard elimination type algorithm, except the first phase, which I wanted to emphasize. All right, so the means of each of the arms we will denote by pi, and we're going to assume that p1 is the biggest. All right, so that we don't have to carry around the argmax. Okay, we're going to define the gaps as usual, delta I, which is basically P1, the first mean minus the suboptimal one, right? Here I is bigger than 2. All right, and we're going to set as usual delta 1 to be the same as delta 2. Okay, so we're treating the first one slightly differently. Now, if we do things in this way, all the deltas are positive, I think. All the deltas are positive. All right. So in order for me to state our theoretical guarantee, we need to have 2 definitions. All right, 2 hardness quantities. All right, that are specific to linear bandits. All right, we're going to give them names H1 lin to remind ourselves that we are dealing with linear bandits. And H1 lin is basically 1 divided by delta I squared. These are not too surprising, but we only go up to D. And I want to highlight this. We only go up to D here. All right, so this is a hardness parameter. The smaller the gaps, the harder the job is. And so this is a certain hardness parameter. All right, and this is a second hardness parameter, H2 lin, which is basically maximum I running from only 1 to D of I divided by delta I squared. Again, I want to highlight that we are only going up to D. We're not going up all the way to K. K is bigger than D. All right. And we have some simple relationships like H2 lin is smaller than or equal to H1 lin. This is the direction that we need. But in case you want an exercise, this is something that you can also prove. Okay, H2 lin here. All right. So this is the inequality that we will need to use to assert minimax optimality. So actually, I was looking at the time there, but the computer has gone to sleep. So I have infinite time. So the theorem is as follows. All right. So our policy is, of course, called OD lin by. So I will put our policy here. This is something that our policy outputs is not equal to the best arm. It is less than or equal to, all right? And I'm hiding lots of constants here and hiding lots of prefactors here, all right, that are immaterial for our discussion. Minus T divided by some constant like 32, hardness parameter H2 lin, and log D. This log D directly comes from the fact that we have log 2 phases, log 2D phases here, all right? So there are some interesting features of this bound here, and then the most interesting one is this log2d here. Okay, so before I talk about lower bounds, I want to talk about state of the art. All right, state of the art in this area of linear bandits, fixed budget best sum identification. I'm not doing fixed confidence. All right, so there is this work with algorithm whose name is Bayes gap. I'm not sure why it's called Bayes gap, but it's called Bayes gap. It's derived by, it was proposed by Hoffman in 2014 paper. They have some guarantee, but this algorithm is not parameter free. For example, I believe you need to know something about the hardness parameter, which is not realistic in practice. Here, this algorithm that we design is completely parameter free. There's this very recent algorithm piece by the group of Kevin Jameson and his students, Hart Samuel et al. This was fairly recent in 2020, new RIPS. And firstly, it's a
stupid question, but you have D less than K, right?
Yeah.
So if I run successive elimination, sorry, successive rejects, why can't I just run successive rejects without exploiting the linear parameterization? Won't I get something comparable in terms of
No,
bounds?
but you will have, there are K arms altogether, right? You probably will get log K here.
Okay, not after, look, if I, okay, so it's like effectively successive rejects with order of D arms.
Yes.
Yeah. Okay.
Yes, and the key here is that our algorithm basically at each point in time successively finds a
Okay,
set.
let me phrase this question differently. So after the first phase, if I do successive rejects, I should get a comparable bound.
Yeah, so yes.
Without doing any of this G, what is it? G design.
G optimal design.
G optimal design.
I think you still need to do the G optimal design to exploit the linear bandit structure.
No, but if I ignore the linear structure and just do successive rejects after the first phase, I think the guarantee should be comparable, right? Am I missing something? Because you eliminated half of the arms, so order of D arms left. And I'm doing successive reject, so the guarantee will be of this order, and your hardness parameters are going only up to D.
Yeah, exactly. The hardness parameters go up to D here.
So if I just do successive rejects after the first phase, I save a lot of computation.
Yeah, that's possible. Yeah, I think so. Okay. There are some things that I'm hiding here. Yeah. There are some prefactors here that are better. Okay, they are better if we do what I just mentioned. All right, there are some prefactors here. All right, so let me just press ahead to talk about the state of the art. So there's this work of Hart Samuel et al. And I think I don't want to talk too much about the comments, but they showed a bound of the order e to the minus omega t to the d divided by h2 log squared d. So there is a slight suboptimality here. All right. And there is this other algorithm called linear exploration, also around the same time, ICML 2021, in which they showed a bound of the order e to the minus omega t divided by h2, slightly modified, and I'm not going to write down the definition, log k. All right, there is this other algorithm as well called GSE, which was proposed by a group by Azizi as well, Nichkai last year, in which they showed a bound of the form e to the minus omega t delta 1 squared divided by d log k. So there's always a little bit of suboptimality in this parameter here. Okay. There are various definitions of the hardness parameter. Some go all the way up to K, some go all the way up to D only. And this part here looks a little bit like our hardness parameter as well. Okay. But the point here is that K can be large, and so your denominator here is large. That results in a small exponent. Okay. So just comparing the order of the exponent, our result is possibly the best. All right, so now I want to talk about the promised minimax lower bound. Okay, and that will take a few more minutes and I'll probably end on time. Okay, so the lower bound goes as follows. Just now someone had already asked like how we formulate the lower bound, what is the meaning of minimax optimality. Now I'm going to repeat myself. So I'm looking at all possible instances V, all right, in the set E. I'm not sure whether you remember the set E, but E is basically the set of all linear bandit instances that I have defined above. So I'm going to be more explicit when I write H1 lin, the hardness parameter, and just so you can recall, the hardness parameter H1 lin is given by the following. Okay. Okay, so our minimax lower bound will be expressed in terms of this hardness parameter. Let's consider the following subset of instances E that consists of all possible instances within this set that I care about, such that the hardness is not more than C. Okay, so these can be thought of as hardness bounded instances. Okay, then our minimax lower bound goes as follows. All right, for all T, C sufficiently large, all right, if I look at the error probability of any algorithm pi, so not equal to 1. 1 is the best arm, just to remind you. All right, I multiply by this factor here, e to the large number, 2700t, divided by h1 lin c, all right, h1 lin this should be new, right? Log D, log 2D. All right, and I look at the worst case possible, worst instance possible across this entire class of hardness bounded instances, and I look at the best possible algorithm. All right, then that is lower bounded by a constant. All right. So this may be a little bit hard to parse, so let me give you a few, let me just try to unwrap this expression here. All right. So let's compare the upper and lower bounds. Compare the upper and lower bounds. So the upper bound of our algorithm goes as follows. All right, so that is basically for all instances, or the instances are called V of new, right? We have the following guarantee. OD lin out not equal to 1. This holds for all instances, right? Roughly speaking, minus omega t divided by h2 lin times log d. Okay, I'm not going to put log 2d, and I'm not going to care about constants in the exponent. I just want to mention that this holds for all instances. All right, so that is the guarantee for the upper bound. Let us try to unwrap the lower bound into a form that is comparable to the upper bound. Lower bound says the following. There is some specific instance, all right, so let me just copy this. So because I'm copying, you can trust that the upper bound and the lower bound look similar, right? So I'm going to say this is bigger than or equal to, or meeting constants. Okay, just making up notation on the fly. H1 lin here, that's the only change here. H1 lin, but this holds for a specific instance. Specific hard instance that we construct in the proof of the lower bound. Specific instance. All right, so if you look closely at the expressions for the upper bound and the lower bound, the only difference is in here, H2 lin and H1 lin. And before I talked about the lower bound, before I talk about the upper bound, I introduced these two hardness parameters, and I gave you a relation between them, okay? The relation between them is that H2 is less than H1. And if you compare the directions of these upper and lower bounds, you will conclude that OD lin, DAI, the algorithm that we proposed is minimax optimal. Now, there are some qualifications I have to make when I use this term, right? It's minimax optimal up to constants in the exponent. In the exponent. So I am not caring, I do not care about prefactors here. And I also do not care about constants here. So in this sense, OD lin BAI, the algorithm we propose is minimax optimal. So this concludes the story, and I still have 25 seconds more. Okay, so here basically we talk, I have some experimental results that I can show if you indulge in me, but I'm standing between you and lunch. So I just want to basically conclude by saying that here we consider a bandit problem, linear bandit problem, and we adopt a fairly straightforward algorithm involving elimination. The only twist is that we do something slightly different in the first phase, and we constantly do dimensionality reduction, and that gives us some improvement in everything that people had done previously. In particular, we get this log2d here. And additionally, we have these hardness parameters that only go up to the top D arms, not all the way to K, which could be very, very, artificially hard. So this also goes up to the top D arms as well. So you can refer to our paper if you're interested in experimental results. Okay, the one line summary of our experimental results is that we come up with some instances so that our experimental results look very good. All right, so we cannot guarantee that this algorithm works very well for all possible instances, okay, because this is only in theory, but when we do the experiments, it looks good compared to everything else on reasonably sized instances for reasonably extensive set of data sets. So this is where I want to stop now because I don't want to stand between you and lunch. Here I talk about linear bandits and I propose a minimax optimal algorithm in the fixed budget setting. Minimax optimal, I need to be very careful with what I say because I have to say that we don't care about constants here, we don't care about constants there, up to constants in the exponent only. Okay, so that's where I will stop now. Thank you very much. That's at the beginning, right?
Yeah, right at the beginning. So I'm just curious to know, is there an application where this specific model arises?
Sure.
Real world application.
People study this extensively, hence their applications. Okay, jokes aside, these sort of things have applications in clinical trials, recommendation systems. You could have many different items or movies, but they only have certain genres or characteristics, and so all the action happens in a lower dimensional subspace or manifold. So this sort of model is widely applicable everywhere. But here we are not really talking about applications. I want to provide a theoretical guarantee.
I have a quick question.
Yes.
Can you pass the sup over E of C in the lower bound?
Okay, so here we are looking at all possible instances that are, here we're looking at all instances that are bounded in terms of the hardness C, okay? So we are looking at the worst case. Okay, so actually in our paper, we have two different statements for the lower bound, all right? This is one of the statements that I find more meaningful because we see the log2d here. But here we are looking at the worst case of the probability of error multiplied by what it should be. I'm bringing it all over onto the side here. And here I'm looking at the worst case product between the probability of error as well as this factor here that involves the hardness parameter as a function of the instance. So I'm treating this entire thing as an entity on its own, looking at the worst possible case. And I'm looking at basically the best possible algorithm. This says that these two things together is bounded below by a constant. So if I move this, roughly speaking, over to this side here, so this basically says there exists a hard instance. All right. For every algorithm, there exists a hard instance. For every algorithm, there exists a hard instance so that the probability of error is lower bounded by 1/6 multiplied by the inverse of this guy here. That's how I pass this.
So if this has a long answer, we can take it up after lunch, but are you going to derive the lower bound or give us ideas of how you come up with the lower bound?
No, actually, the lower bound is not so difficult to derive. It comes from standard bandits. So I'm not going to derive this because it will take some time. And I think if you understand the basic ideas for K-arm bandits, the not linear bandits, then this is rather straightforward to derive. The key here is that you can linear bandits is a generalization of standard K-arm bandits. So if we set all the coordinates, if we come up with a step, if we basically particularize linear bandits using the standard basis, you only focus on the top D instead of all K dimensions, this is what you can get. So it's not so difficult to derive.
There are no other questions. Let's thank Vincent again.